All right, it's 9 o'clock. Okay, so we're going to start the class for today. And just a quick reminder that the quiz will close on September 21st at noon. So make sure to finish the quiz online. Any questions? Okay. All right, so let's continue our discussion about bonding concepts. One sec. Okay, so last time we kind of stopped here, right? So this question that for each of the following molecules show the direction of the dipole polarities and also indicate which ones have permanent dipole moments. Right? And these are the 5 examples. So there are 2 things you need to consider. The first thing is whether this molecule has polar bonds, right? And how do you determine if they have polar bonds? You compare the electron activities. If the electron activities differ, then you are going to go from the lower ones to the higher ones, right? Going from the partial positive to partial negative. Then you determine the geometry of the molecule. If the geometry is such that it's symmetric, then the dipole moments, the dipole bonds will cancel out, right? For example, HCl, hydrogen has a low electron activity, so it's going to be partially positive. That means chlorine is going to be partially negative because the whole molecule is neutral. So you're going to draw an arrow like this, right? Going from partially positive to partially negative. And this molecule only has 2 atoms, so it's not symmetric. That means this molecule will have a permanent dipole. And chlorine, both of them are chlorine atoms, right? So they have the same electron activity. That means the bond is not dipole. The bond is not polar, so this molecule is non-polar. And SO3 molecule, sulfur trioxide. Sulfur has a low electron activity, so it's going to be partially positive. That means the oxygens are partially negative. So that means the bonds will go from sulfur to oxygen, sulfur to oxygen, sulfur to oxygen. But this molecule is trigonoplanar, meaning it's like an equilateral triangle. Well, meaning it's a triangle. Doesn't necessarily to be equilateral, but in this case it's equilateral. And that means the vectors will cancel themselves out. That means the molecule does not have a permanent dipole. Methane, CH4, carbon has a high electron activity, so it's going to be partially negative, partially positive. So the dipole will go this way, go this way, and go this way, and go this way. And this molecule is symmetric. That means it has polar bonds, but not permanent dipoles. And lastly, we have HF, hydrogen sulfide. Hydrogens are partially positive, and sulfur is partially negative. So we're going to have a permanent dipole that goes this way. And we have 2 polar bonds, and this molecule is permanent dipole. Any questions? All right. So 2 parts: whether the bonds are polar, and whether the molecule has a permanent dipole. All right. So let's continue our discussion about covalent molecules. So how do you actually determine how they share their electrons? When 2 nonmetals react, right, the first keyword is nonmetals. Right? So on the right side of the periodic table, to form a covalent bond, they share electrons in a way that both nonmetals attain noble gas configuration. So another keyword is noble gas configuration. So this shouldn't be too hard for most of you. So the first row is going to be helium, right? So helium requires 2 electrons. So in order for hydrogen to have 2 electrons, they can share their 1 electron, then we have 2 electrons. So when they share, this hydrogen consider these 2 electrons being kind of its valence electrons, and the other one does the same. Then they attain the noble gas configuration. For the second row, it's going to be A electrons, third row L electrons, right? So on and so forth. Okay. For ionic compounds, when a nonmetal reacts a representative group metal, right? 1A, 2A, alkaline as metal. To form a binary, another keyword is binary. So we only focus on binary ionic compound. The ions form so that the valence electron configuration of the nonmetal is completed and the valence orbitals of the metal are empty. Right? So the difference is the first one they share in order to form noble gas configuration, while the second one is they completely lose or gain an electron to attain noble gas configuration. For example, sodium 1s2, 2s2, 2p6, and 3s1. Sodium completely loses this electron such that it becomes 1s2, 2s2, 2p6. That is a noble gas configuration for neon. On the other hand, chlorine has one electron hole here. That means chlorine will gain this electron to fulfill its 3 p orbitals. And this chlorine then becomes similar to argon. So this will be similar to neon. This will be similar to argon. That's how they actually complete the noble gas configuration by completely losing an electron for sodium, completely getting an electron for chlorine. Right. So you're going to have Na plus and Cl minus. Right. Noble. This is the electronic configuration in drawing for neon and for argon. Okay. And the number and the direction of the electron transfer depends on 2 parts. The electron activity, right? The higher electron activity against the electron, that would be non-metal. On the other hand, the lower electron activity element, which will be the metal, loses electron. For example, oxygen is much greater than that of calcium, so oxygen will gain electron, calcium will lose electron. Because of this large difference, right? The difference is like 1.0 to 3.4. Will be transferred from calcium, electron will be transferred from calcium to oxygen, right? So eventually we're going to have calcium losing both of its 4s electrons, while oxygen will get electrons to fulfill its p orbitals, right? And note that oxygen needs 2 electrons to fill its 2s and 2p, right? In order to get to 2p6. And to achieve the configuration to neon. And by losing 2 electrons, calcium can achieve the configuration of argon. 2 electrons are thus transferred. Losing 2 electrons, gaining 2 electrons, right? So this also gives you what? Stoichiometry. For example, if we change calcium to sodium, that means oxygen still needs 2 electrons, but sodium can only lose 1 electron. That means you need 2 sodiums per oxygen, right? So sodium oxide is Na2O, right? So that also gives you stoichiometry, the ratio between the elements, basically. All right, and that should be kind of some kind of a recap of your high school. Because aluminum has the electronic configuration of neon, this is in noble gas configuration, 3s2, 3p1. You must lose 3 electrons to form aluminum 3+, and thus achieve neon configuration. On the other hand, oxygen still needs to gain 2 electrons. That means the ratio between oxygen and aluminum will be aluminum 2 in order to lose 6 electrons, oxygen 3 in order to get 6 electrons. So aluminum 2, oxygen 3. So these are some, common final configuration when the metals and non-metals achieve the noble gas configuration, right? So the group 1A will lose 1 electron, so they have plus charge. Group 2A, alkaline earth metal, will lose 2 electrons. Group 3A will be getting 3 electrons, losing 3 electrons, and you can see we don't have anything here. Why? Because these are more like metalloids, like boron. What's beneath boron? Gallium, those are more like metalloids. So they don't completely lose electrons, they still share bonds. On the other hand, we have group 6A, chalcogens, and these gain 2 electrons. 7A are our halogens, and 1 electron. And lastly, they wish their corresponding electron configurations. Noble gas electronic configurations. All right. However, like I mentioned last time, right? If the story is that simple, then this chart wouldn't make any sense. However, when we did the experiment and measured the ionization potential and electron affinity, we realized this doesn't add up, like I mentioned last time. For example, magnesium oxide, which contains magnesium 2+ and oxygen 2- ions, is very stable, but the isolated gas-phase ion pairs are not stable. It's not energetically favorable. Just by looking at numbers quickly, you can see magnesium, the first ionization potential is about 750 kJ per mole. But oxygen, the electron affinity for the first electron is only -150 kJ per mole. That means magnesium will not lose that electron to oxygen in gas phase. It doesn't provide enough energy to get that electron out. And this is a trick that really the formation of the corresponding ionic compound requires small steps in addition to just the simple electron transfer. And in the solid state of an ionic compound, the ions are relatively close together, and many ions are simultaneously interacting, right? A picture like this. You can imagine like the minus will be oxygen, and the plus will be aluminum or calcium, or chloride and sodium. And what happens is this minus charge is adjacent to 4+ charges. Right? Will be, for example, calcium, and oxide. And then the plus charges are also surrounded by negative charges, right? So you can imagine there will be a negative, non-negative here. So you can grow the lattice larger and larger and larger. And what you'll see is you have pairs of repulsion and attractions. So the negative charge will be attracted to the positive charges, right? Oxide and calcium, they are attracted. On the other hand, the oxide also get repelled by the surrounding oxides. And of course, this bond is shorter than this bond, and Coulombic force decays inversely with distance, so the attraction is stronger than repulsion. And indeed, it is this sum of attraction and repulsion that gives more energy into the system that actually finally forms the ionic compound. Indeed, it is this ordered near infinite packing of positive and negative charges drive the formation of ionic compound. Right. So we have a difference about 600 kilojoule per mole, and we need to get this energy in order for magnesium to lose its first electron. It's around 750, and we have minus 150 here. So we are in depth for 600 kilojoule per mole energy. On the other hand, the formation of a complete packed lattice actually gives this extra energy. And this is what we call the lattice energy. It's another keyword for today. And lattice energy is defined as the change in energy that takes place when a separate gaseous ion, right? Imagine we have calcium 2 plus and oxygen 2 minus, only a pair. And taking these pairs and get a mole or 2 moles of this pair and sink, precipitate, or actually packed into a really ordered lattice, right? Packed to form an ionic solid. So lattice energy is formally defined as gas phase separate ions going to solid phase. Right? This is something for you to actually remember. That is, the lattice energy is going from the individual gaseous ions, right? 2 parts. These need to be ions. So not gaseous atoms, but gaseous ions forming into a solid corresponding ionic compound. This is the definition for lattice energy. So if you just look at this example here, lithium solid, right? Lithium is a piece of metal, and fluorine gas. Well, to balance the stoichiometry, you only need half equivalence of fluorine gas. This reaction is not the lattice energy. This reaction is not the lattice energy. But it also contains lattice energy if you look at if you break out the process into different processes, right? So first, because we need gaseous state, so we first sublime lithium solid into lithium gas. And then the second step, so the first one is more like sublimation, phase change, right? And the second equation is ionization. We remove the electron from lithium gas into lithium plus gas plus electron. This is the first ionization energy of lithium. For fluorine, because it still has a fluorine-fluorine bond, while we can only have the single atomic like negative ion. So first we need to break the bond. 1/2 F2 gas into a F gas. So this is bond dissociation energy or bond breaking energy. It takes about 77 kilojoule per molecule. And lastly, the fluorine gas will get an electron to form F minus gas. This is called the electron affinity, which releases energy because fluorine is really electronegative, about minus 328 kilojoule. Lastly, we have the lattice energy. Right? Only the last equation is the lattice energy. That is the lithium plus the cation in gas phase plus F minus the anion in gas phase to form the solid phase lithium fluoride solid. So if this were changed into gas, right, only forming ion pair is not the lattice energy. You need 2 gaseous phase ions in one ratio, and then you can have stoichiometry balance into the solid. This is how we define as lattice energy. And as you can see, the number is huge here, right? Minus 1047 and 47 kilojoule. And hence, the overall reaction, the original reaction that goes from the elemental form to the final product has an energy about minus 617 kilojoule. If you actually sum up the numbers above the lattice energy, you quickly realize the number is positive. That means without forming the lattice, this reaction will not be spontaneous, will not be exothermic, right? Just sum up 161, 520, 77, minus 328. The number here, the sum is not negative. That means the reaction is not exothermic, it shouldn't be happening. Right, the last part, the formation of the lattice really gives you a huge driving force for the formation of the final ionic compound. Any questions here? All right, let me recap. The first one is called sublimation, right, going from solid to gas. The second one is called ionization, losing electron. And the first ionization energy, of course, only lose one electron. And the third is called bond dissociation energy, you break the bond, right? Or bond breaking energy. And the fourth is called electron affinity of fluorine. And lastly is called the latest formation energy or latest energy of lithium fluoride. Okay? All right. And of course, you might not like itemized list. So you can also look at kind of a gap, more like a flow diagram. Right, so we start with lithium solid and fluorine gas in their elemental form, right? Lithium is a metal, fluorine is a gas. Then you can sublime lithium solid to gas, and then again you can ionize lithium, right, by pumping in energy, and then you can break the bond of the fluorine, and you electron affinity give electron to fluorine, and fluorine releases energy, and finally a huge step of latest energy, going from the gas phase ions into solid phase. And the overall reaction, everything should be balanced here, is this arrow here, minus 670 kJ per mole. And this is called, what diagram was this? Van Hoff diagram. The name for this is Van Hoff diagram. You don't need to memorize the name, but it's called Van Hoff diagram. Okay? And of course, we can extend the latest, right? So it doesn't just look like two-dimensional, it's actually three-dimensional. And as I mentioned last time, we have something called the Madelin constant that actually can calculate what will be the overall interaction energy, not compared to just pairs of ions, right? Which you don't actually need to know for this class. And the structure of lithium fluoride, right, represented by balls and stick model. So these are the balls. So you can imagine that these are noble gases, right? Ions of noble gas configurations, so they are kind of spherical. And the lines are really not there. They are just drawn for you to see, right? Because these electrons are really spherical. Note that each lithium plus is surrounded by 6 fluoride, and each fluoride ion is surrounded by 6 lithium plus. And represented by ions also showing spheres. This is more actually physical, because actually electrons are really spherical and extended into space, right? So this actually is a better depiction, but this is easier to see, right? So we can actually see the depths. Why? In this case, it's very hard for us to see the second layer. Structure is determined by packing the spherical ions in a way that both maximize the ionic attraction and minimize the ionic repulsion. And as I mentioned in the class on Monday, we will learn a lot more about this, right? So again, a quick preview, you can see that by having 6 surrounding, right? So if you take a look at this purple sphere, this is a lithium plus ion. Yes, 1, 2, 3, 4, 5, 6. 6 chlorides surrounding this. So how do we say this lithium? Lithium is in an octahedral environment, right? Because we have 6 bonds. And if you actually draw this structure, you can see we have 1 phase here, 2 phase, 3 phase, 4 phase, 5 phase, 6, 7, 8. Hence octa, right? Octahedral means 8, 八面体。所以这个 lithium formally 在一个八面体的环境里面。So we call this an octahedral hole. It's inside a hole that will form the octahedral. In addition, if you look closer at the fluorines, you can see that we have 1, 2, 3, 4, 5. 5 fluorines. Just look at, not looking at this last layer. Just looking at this square here. We have 5 fluorine here. Looking at this second layer square, we have 4 fluorines, and they are kind of 90 degrees from each other. And lastly, we repeat the first layer. So again, we have another 5 fluorines on this face or this plane. How do we call this? This is an ABA pattern, because the first layer and last layer are the same, while the middle layer is different, right? Just by looking at the fluorines, only look at the green spheres. And we call this an AB packing. You'll learn much more about this when we talk about liquids and solid. And AB pattern is a synonym for cubic closest pack. It's also a synonym for face center cubic. They are the same. AB pattern, CCP, cubic closest pack, CCP, and phase center cubic, FCP. They are the same thing. Don't worry, it's a lot. We will come back to this. Okay? Latest energy calculation. How do we actually calculate this, right? The energy released when the gaseous magnesium 2+ and oxygen 2- ion combine to form the solid magnesium oxide is much greater than that released when the gaseous sodium plus and fluoride minus combine to form solid sodium fluoride. So the latest energy for magnesium oxide is much greater than sodium fluoride, and this shouldn't be surprising, right? Just by looking at the charge. We are putting a bunch of charge into a lattice. The more charge we have, the stronger the Coulombic attractions. Of course, the stronger Coulombic repulsion as well. But attraction will win. Otherwise, we won't have a lattice, right? So the attraction is stronger for 2+ and 2- than 1+ and 1- by about 4 times the magnitudes, right? Because charge multiplied by charge. So 2+ multiplied by 2- we have 4-. 1+ multiplied by 1- we have 1-, right? So formally, the latest energy of magnesium oxide should be 4 times that of sodium fluoride. But of course, we have a difference in distances as well, right? So it's about 4 times just by looking at the charge, right? So let's compare the real experimental value measured by experiment. Ionization energy. That's wrong. Sorry, that was wrong. Not the Van Hoff cycle. It's Born-Haber cycle. It's a Born-Haber cycle. Okay. Quick comparison of the latest energy. You can see that for sodium fluoride, latest energy is at around -923 kJ per mole. While the latest energy for magnesium oxide is about -3,916. So if you multiply this number by 4, you're going to get about 36, about 92. So if you multiply this number by 4, you get 3,692. While if you look at latest energy, it's about 3,916. So indeed, you can see latest energy is actually slightly more by 4 times, right? Which makes sense just by looking at electrostatic interactions. All right, so let's quickly go through the whole Born-Haber cycle. Not the Van Hoff cycle, I said it wrong. It's the Born-Haber cycle. Max Born and Haber, right? Haber is the person who actually invented Haber-Bosch process, the fixation of ammonia, fixation of nitrogen to form ammonia, N2 plus 3H2 to form NH3, 2NH3. While Born is the person that gives the Born interpretation, right? The square of the wave function is the probability density. All right, so let's look at the 2 cycles again, kind of a recap, right? So this part is the magnesium, this part is the magnesium oxide, and this part is the sodium fluoride. So after getting them into the gas phase, the first thing we need to do is ionization of the corresponding metals, alkaline metal and alkaline metal. This one, as you can see, the energy is about 495 kJ. So this energy is not the ionization energy of magnesium. If you look at this number closer, it's the 2 ionization energy of magnesium. So you need to watch out for this. If this happens to come up on your homework or on the exam, the ionization energy of magnesium into magnesium 2+ in gas phase need to be the sum of the first ionization energy and the second ionization energy. Right. So you actually need magnesium in gas phase to give you the first electron, magnesium plus gas phase plus electron. And then you have the second reaction, that is magnesium plus gas phase to give you magnesium 2+ gas phase plus electron. And we say the first energy is ionization potential ionization energy 1. And the second one is the ionization energy 2. Hence, if you sum this up, the final ionization energy is ionization energy 1 plus ionization energy 2. And is this number, which is 2,180. 2,180 kilojoules. So watch out for this. It's not just taking the simple ionization energy, because magnesium need to lose 2 electrons. And these 2 electrons is not just a simple multiplication of the first number by 2. They are 2 different values, right? Okay, so watch out for this. So this ionization energy need to be the corresponding first ionization energy and second ionization energy of magnesium. Okay, but sodium is easy, right? Just first ionization energy. All right. The second one is what? Is the breaking of the bond. We have half of O2, so we need to make it into O. So bond breaking energy or bond dissociation energy of O2. But watch out for this also. We only break half a mole, so we need to divide the number by 2. So that means, can you erase this? Or I write it on the other side. Right. That means if this happens to be your homework or it happen to be exam, it's going to give you the bond dissociation energy of O2 is actually twice of that energy. That will be 494. And do not directly take this number because we only have a half a mole. Right? We have half O2 gas O into O gas. Hence, the energy for this process should be 494 multiplied by 1/2. It will be 270. 247. So watch out for this. Right. So make sure don't drop the ratio here. Okay. So it will be the same for fluorine, right? We only have half of a fluorine. So this number 77 is actually not the tabulated energy. The tabulated energy will be 154, but we are only breaking half of a mole. So we need to divide this number by 2. So you get 77. All right? And electron affinity for fluorine is easy, right? So you're getting 1 electron. So this will be just the electron affinity of fluorine, which will be minus 328. Again, for oxygen, it's tricky, right? You have 2 again, right? Similar to magnesium. Can you erase this? You haven't got it? Raise your hand if you haven't got it yet. For oxygen, it's the same. And definitely bond-Haber cycle will appear on your homework and also on the exam, right? This is very important. So right now we have, not fluorine, sorry. Oxygen gas. You need to finally get to oxygen 2 minus, right? Because we have 2s2, 2p4. You need to gain 2 electrons. So that means it's going to gain the first electron to give you O minus gas. And then O minus gas, then gain the second electron, then give you O2 minus gas. And the energy for the first one is called the electron affinity 1, EA1. That is the energy released when O gains the first electron, and the second one will be EA2. Right? That means the number here, that is 337, is the sum of this. And which will be 337. Okay, watch out for this. And by looking at this number, you quickly realize one thing is weird. Why? For ring, when we say that electron affinity is for an element to gain an electron, it releases energy. So this number, electron affinity, is usually negative. Right, so it makes sense for fluoride. Fluorine gains an electron to become fluoride, it releases energy because electrons are kind of energy. But if you look at oxygen, the electron affinity for 2 electrons is actually positive. And let's go back to our chart. What time do I have? How much time do I have? 20 minutes? That's good. Okay. If you look at our chart, the first electron affinity for oxygen is about minus 150. About minus 140. Right? So that means EA1 is about minus 150. Right? Just by reading out of this chart here, right? So you quickly realize something really weird. That is, the electron affinity for oxygen minus is much greater than 0, which is about, if you add these two together, about 900. Right? Because 900 minus 150 will give you about 750. I'm just doing the math quick, so I didn't sound the number correctly. So you realize this is something really weird about oxygen. And it actually is something weird about oxygen. That is, it hates to get the second electron. So we like to think about oxygen being very easy to reduce. That's not true. The first reduction of oxygen is easy, to form superoxide. And it happens in our body, actually. But the second reduction of oxygen to form peroxide is actually a very endothermic process. It doesn't like to happen. And it happens in our body too, right? We are breathing oxygen right now. And our hemoglobins, 红血球, it carries your oxygen, that's why it's red, right? And what will happen is oxygen likes to gain the first electron. So it's going to go from O2 into O2 minus, we call superoxide. And superoxide is very reactive. It's going to destroy a lot of things in your body. Destroy your cell, make your cell into cancers because it is breaking some part of your cell, making it not functioning well, right? So indeed, that's why our body has a really good protection mechanism to protect you from superoxides. This is something really interesting about oxygen. Right? The second oxidation electron affinity is positive, not negative. Hence, if on your homework or on your exam, you happen to write down the electron affinity, make sure it's going to be positive for all, right? Because the first ionization affinity of oxygen is negative, but the second electron affinity of oxygen is very positive. Hence, this number is 737 plus, not minus. And lastly, we have the huge lattice formation energy and the centrifuge lattice formation energy. Hence, lastly, we're going to get the overall energy change for magnesium oxide is minus 600 O2 joule, and for sodium fluoride it's minus 570 joule. Right? So it's kind of funny that we have such huge lattice energy, 4 times that of sodium fluoride, but the final reaction energy is the same. Right? Because oxygen is not doing a good job getting electron. Right? And of course, ionization energy is also large for magnesium. So interestingly, it kind of balance out, right? The electronic contributions, electronic transfer contributions, balance out the huge lattice energy, finally such that the overall reaction energy is the same. Okay, I kind of skipping ahead, right? So that's good. Okay. All right. So as you can see, the ionization energy is going to be positive. Electronegative affinity does not necessarily to be negative. Fluoride is negative, but oxygen is positive. Hence, in order for reaction to really happen, for sodium metal and fluoride metal gas to react, for magnesium metal and oxygen gas to react, is really the lattice energy. We have a huge stabilization by packing a lot of charges into solid state. All right, and of course, you can imagine lattice energy is going to decay as we increase the size. So if you keep the charge the same, right? But all we do is lithium plus, chloride minus, lithium plus, chloride minus, etc. But we make the ions larger and larger and larger just by using a simple Coulombic force expression, Coulombic energy expression, QQ divided by 4 pi epsilon naught R, or KQQ divided by R. We sometimes make this K. As we make the radius larger and larger, distance gets farther and farther, and Coulombic energy decays with energy, so you can see we have an inverse decay in the extremely major lattice energy. It's going to be the same as we keep the size of the anion but make the cation larger and larger, we also decreases the lattice energy. And for each cation, the anion increasing the size of the anion decays the lattice energy almost inversely. So it makes sense from the Coulombic energy sense. And there's a caveat. The caveat is that we are assuming they pack the same way, but that's not the case. And as you can see, lithium, sodium, potassium, why did we drop rubidium and cesium? It cannot last so large that they don't pack in a closest pack anymore. They are not CCP, so they cannot be compared. All right, so I'm going to ask you to actually do this one, and I ask for a volunteer. So actually, some of you emailed to me that you missed the attendance or you didn't key in the attendance. I do not offer for makeups, but that's fine. All you need to do is answer questions in the class, and you can get a makeup. right? So that's kind of how I make up your attendance. If you didn't attend or you just didn't key in the attendance, that's fine. Just answer questions in class and you can get a bonus point. All right. So the energy released from the reaction between 1 mole of cesium and 0.5 mole of fluorine gas is 553.5 kJ per mole. Find the latest energy of cesium fluoride given that the ionization potential of cesium of the absolute electron affinity of fluoride, the enthalpy of sublimation of cesium, and the bond dissociation enthalpy of fluoride are 374.7, 328.2, 76.5, and 158.5 kJ. All right, I'll leave this to you. About 5 minutes. Okay. Okay, so yeah, any volunteers? Or you guys still need more time? 负306.3是 是那个 latest energy 吗？负306.3，我们看一下是不是负306.3？好像是负756.9。好，没关系，错是好事，错代表有些地方我们可以再review 一下啊。Okay, so his answer was minus 306. That's fine, which is kind of different from this chart I have here. Let me double check. Yes, it's okay. That's great. Means that we still have something to talk about in this diagram. Otherwise, it will be too easy for me. All right. So let's look at the numbers here. So first, the trick of this question is it gives you all the number in positive. So as you can see that it purposely gives you absolute energies. Why? Because it wants you to determine the sign. Does this reaction release energy, or the series reaction gain energy, right? Positive, negative, or positive respectively. So first, you can see that the first energy gives is the ionization energy of cesium, so definitely should be positive. Electron affinity of fluorine should be negative, so this number is actually negative. The enthalpy of sublimation is positive, right? You need to give it energy in order to sublime it, so this will be positive. And lastly, dissociation enthalpy, because this is energy, heat, is fluorine is positive. You need to give it energy to break bond. However, this is for a mole of fluorine. We only have half a mole of fluorine, so this number needs to be divided by 2. Okay, so let's check out the numbers. So the first number we have is energy of sublimation. Oh, it's this number. Okay. 76.5, right? That corresponds to the positive 76.5. The second one is what? Is the ionization energy of cesium, so it should be positive, which will be this number, plus 375.6. And the third number is the bond dissociation of fluorine, but only half a mole of fluorine, so 158.8 kJ per mole is going to be half of that number, 79.4. And the fourth number will be the electron affinity of fluorine, which is negative, not positive. So it will be the second number, 328.2, but negative with this number. All right, and lastly, the energy is the latest energy. And the reaction overall is the release, right? Energy release, hence this number 553.5 is positive, but it's released, so it should be negative. So the overall reaction is negative. So if you balance out the equate the equation, you realize the latest energy is minus 756.9 kJ per mole. And that's okay. If you get it wrong, you still get a bonus point. So don't worry. All right. So feel free to try. It doesn't hurt to try. If you didn't get the same number, minus 556.9 kJ per mole, please make sure to review this chart again. This will definitely occur in different forms for your quiz and for your exam. Right? Make sure you actually can get this final number correct. Okay, any questions here? All right, I have about 5 minutes. I'm going to quickly go through the last part, and then we can sum up bounding concept 1. Okay, so let's go back to like a very similar to HF, right? So how do we actually characterize or quantify a bond? We know a covalent bond could be polar or non-polar depending on the difference in electronegativity, but how polar is polar, right? That is called the percentage ionic character of the bond, right? We did it before by measuring the difference in dipole moment. Theoretical dipole moment, if they were fully ionized, and really measured experimental dipole moment for their partial charges, right? And the ratio of this multiplied by 100% is called the percentage ionic character. As you can see, as we go to the more and more difference in electronegativity between two elements, we get stronger and stronger ionic factors. So like IBr, which is iodine bromide, they are in the halogen group. So they have only small difference in electronegativity, about like 0.3. The percentage ionic character is almost 0. So this one is almost non-polar, slightly polar. But if you go to really huge difference, lithium and fluorine, cesium and fluorine, then you go to really huge, almost 100% ionic character. This shouldn't be too surprising. The more electronegativity difference, the more percentage of ionic character, right? And lastly, and in the next class, we'll start to talk about what's covalent bond anyways. How do covalent bonds form anyways, right? Chemical bonding can be as forces that cause a group of atoms to behave as a unit, right? Positive charge and negative charges, right? For example, methane CH4, about 1,652 kJ of energy required to break a mole of methane into separate carbon and hydrogen. You just take a piece of charcoal and hydrogen gas, right? Just measure the heat released. The energy of stabilization of CH4 is divided equally among the 4 bonds to give an average CH bond of energy per mole of CH bonds, right? So you take this energy of the formation energy of methane, 1,652 divided by 4. So every bond, every CH bond should be 413 kJ per mole. And this is one of the strongest energies for the covalent bonds, right? So methane is something really hard to study nowadays. And if you take a look at CH3 chloride, experiments show that about 1,578 kJ of energy is required to break 1 mole of gaseous CH3 chloride molecule into gaseous carbon, so on and so forth. So hence, finally, you can actually get the CCl bond energy is about 339 kJ per mole. Because from previous, we know CH bond energy is 413. We have 3 CH bonds. So we have 3, now be some numbers here. And hence, we can get CCl bond is about 339 kJ per mole. So this is kind of a cycle, right? We can actually measure CH4, the pure one, to get CFH bond energy, and then use this in a mixed element to get a CCl bond energy, right? So you can see that energies are kind of like, you can tabulate the energies. You can use one to get one of the energies and use that to get the second of the energies. And indeed, this is what we call, what's the name? Hess's law. And we'll come back to Hess's law as we go through thermochemistry. Right? That means we can actually tabulate different bonds and then use that to calculate different energies. Right? Hence, finally, we can reach a table like this by doing different experiments. Right? So HH bond is at 432 kJ per mole, and HF, and so on and so forth. And it wouldn't be surprising to you, right? HF bond energy is higher than HH because this is formally a polar bond. The more polar, the more attraction, right? Partial positive, partial negative. Well, as you go from HF to HCl, H bromide, H iodine, H gets smaller and smaller. Why? Because they get larger and larger and larger. Coulombic repulsion gets weaker. Coulombic attraction gets weaker and weaker and weaker, and so on and so forth. And of course, you get to multiple bonds, the energy gets stronger and stronger. Because formally, you need to break 2 bonds, right? And lastly, you can write out the sum of the bond breaking and sum of the bond formed by reading the table here, right? You are breaking HH-FF bond, so HH energy here, FF energy here, and you are forming 2 HF, right? HF energy here, right? Twice of that. Then you can write down the energy, the enthalpy of the formation of this reaction is minus 544 kJ. Just by reading out of the table here and get the stoichiometry correct. All right, and that's all for today.